Let's take a look at an optimization problem. This is from section 4.5, number 17. Optimization is a very important application of derivatives. It's a challenging application. As we look at various examples in 4.5, one thing that I'm sure you'll notice is that from one example to another, they can often look quite different, but there are some important commonalities that we'll keep in mind, and the approach is going to be the same no matter what the optimization example. So let's look at this particular one. It says a rectangle is constructed with its base on the diameter of a semicircle with radius 5 and its other two vertices on the semicircle. What are the dimensions of the rectangle with maximum area? So anytime you look at an optimization problem, it will, in one way or another, ask you something about the maximum something or the minimum something. So you're trying to, usually it's geometric in nature. And so in such cases, you're trying to find the best shape to, maximize area or minimize volume or whatever the case may be. Now, it doesn't always have to be about geometry. You might have something where you're trying to minimize cost. But geometric examples are very common here, and this is one where we are going to use some familiar geometric relationships to solve this. Now, first thing you want to do with any optimization problem is read through probably at least a couple of times and make sure you understand exactly what it's asking you and what information it's giving. Now, I sketched a picture down here. This was not given in the textbook, but the information in the paragraph here describe what we're talking about. So we've got this semicircle of radius 5. I centered it at the origin for convenience, and they tell us that two vertices are on the diameter. Okay, so those are on the x-axis, the way that I drew that. And the other two vertices are on the semicircle. So we've got this kind of setup. Now, there are lots of rectangles that meet that description. I drew one, but you could make it a little narrower and taller. You could make it wider and shorter. As long as it meets this description. They're looking for, among all of those rectangles, they're looking for the one that has the maximum area. So notice I wrote down here y equals the square root of 25 minus x squared, and in parentheses I wrote constraint. So that's the equation for that semicircle. So the vertices on there would have to satisfy that equation. So that's a constraint, meaning it's giving a relationship between the variables that we must follow. For all of our rectangles that we're considering, they must meet that constraint. Okay, so notice here, by the way, I labeled a certain part of this picture as x. It's really half of the length of this rectangle, but the x-coordinate of this vertex up here, okay, would be x, and the y would be equal to this. So we'll keep in mind that x is not the entire length, it's half the length. Okay, so with that in mind, and you might, by the way, use different variables, you might label things differently. As long as you're doing it correctly, you'll get to the same answer, even if the work might look a little bit different based on how you set things up. So the area based on my x and y here, would be 2 times x times y. Now I did a substitution here using this constraint to get this area in terms of one variable. Now that's referred to as the objective function, this area. And in every single optimization problem, you want your objective function in terms of one variable. Always, always, always. So that's something that all of these examples have in common. That's a step you will always take. Maybe depending on the example and how you define things, maybe when you write out your objective function, it's already in terms of one variable. But frequently you'll have to do a substitution, and that comes from the constraint. I wrote here the domain. Now, to be precise, this 0 and 5, so notice here, based on how I labeled x could be as small as 0 or as big as 5, and still, still satisfy this description. But really, if it were 0 or if it were 5, we no longer truly have a rectangle, because then we've got a dimension that's 0. But this is how I'm going to write the domain, and we'll just keep in mind that 0 and 5 are not going to give us that maximum area we're looking for. Okay, so once we have our objective function in terms of one variable, now we want to take the derivative. So here's where the calculus comes in. Here's where this becomes an application of derivatives. We take the derivative, and what we're looking for is, we're looking for the set of critical points, okay, any critical points in our domain. What we find in this case, once we take the derivative using the chain rule and simplify, we find that there's 2 values of x that make that derivative 0, but one of them's negative, so we're going to reject that one. So the only one that we're actually interested in is this positive square root of 25 over 2, which is approximately 3.54. Now you can go back and check that, if we were looking, we're really looking for absolute maximum, right? The absolute maximum area. Remember, in our approach to finding absolute extrema, we consider any critical points, and we also consider the endpoints. Well, in the endpoints, we get an area of 0. This does not give us an area of 0. So that is going to be our absolute maximum. And now the question asks for the dimensions. So just to wrap this up, we want to make sure we answer the question that's asked. That's an important thing to remember. Well, in any word problem, really, but in optimization problems in particular, you want to make sure that you answer the question. Sometimes they might say, what is the maximum area? Or it might say, find the dimensions. Or maybe it just says, find the length. Or, it really can vary from problem to problem. So be sure that you answer the problem that's asked. So x is approximately 3.54, or that, to be exact, it's the square root of 25 over 2. The length of this rectangle is double that. And as it turns out, the width, if we substitute back into our constraint, the width is the same as x. So what we have is a rectangle that's twice as long as it is wide. And that completes this optimization problem. I hope you found that helpful. Again, keep in mind the things that are consistent among optimization problems, which are, you've got a description. Usually you want to set up a picture that, if it's not already given to you, identify any constraints, get your objective function in terms of one variable, think about the domain, find critical points, and then based on the critical points and the endpoints, decide where is that absolute maximum or absolute minimum, as the case may be. And finally, did you answer the question that was asked? I hope you found that helpful. I will see you in the next video.